Hi there, and welcome from Ventura, California to today's webinar, Autonomous Vehicle Safety, How to Test, How to Ensure. Day one of a two-day series sponsored by NovAtel, Spirent Communications inside GNSS and inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the topic at hand. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all three of our panel members. Now, we've invited you, along with over 650 professionals across 50 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher inside GNSS and inside Unmanned Systems, would like to take just a moment to welcome you and introduce our sponsor and main moderator for today's session. Over to you, Richard.
Thanks so much, Laura. Appreciate that. Welcome all. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, NovAtel, I extend a warm welcome to our audience from around the world for today's virtual workshop on autonomous vehicle safety. We're delighted you're with us today. Now, I'd like to introduce Natasha Wong-Ken, who's the product manager of positioning engines at NovAtel, for some opening remarks. Natasha?
Thanks, Richard, and hello, everyone. I want to first welcome you to this webinar on autonomous vehicle safety. I'm really happy that you could join us today. And we've already seen the adoption of vehicles at various levels of autonomy operating on public roads. So at NovAtel, we know that as this adoption continues, it will be crucial for us to address safety and integrity in all of the solutions that we're providing. So today, our speakers are going to highlight the challenges that the automotive industry is facing when it comes to balancing these integrity risks with solution availability, and then how to overcome the need for hundreds of millions of miles of drive testing that we need to bring these solutions to market. To address some of these challenges, NovAtel is actually leading the way in advancing studies of integrity for precise positioning in automotive, and we offer products that range from high-end hardware solutions for ground truthing to software positioning services that are scalable for production-level deployment. The speakers today bring with them an abundance of knowledge, and they're going to walk us through GNSS positioning fundamentals, integrity concepts, and validation principles. We have a really exciting webinar ahead of us, and I'm looking forward to hearing from the audience. So I hope you enjoy it. And with that, I will pass it back to you, Richard.
Thanks so much, Natasha. Now, I'd like to introduce our moderator for today's webinar. Alan Cameron is the editor-in-chief of Inside GNSS and the PNT editor for Inside Unmanned Systems. He's covered the GNSS, PNT, and autonomous industries as both a writer and editor since 2000, focusing on technical issues around continuous, reliable positioning and navigation. Alan, the floor is yours.
Thank you, Richard, and welcome everybody around the world. It's great to see international attendance as always. Autonomous vehicle safety, how to test, how to ensure. As Yogi Berra famously said, predictions are difficult, especially regarding the future. And we're reminded in our everyday life nowadays that just how true that is. But in regards to autonomous vehicles, this also holds particularly true. We are going to be riding in autonomous vehicles sometime soon, and certainly our loved ones will be during their lifetimes. How do we ensure that everyone is safe? As Natasha just said, hundreds of millions of miles of testing, and you'll hear another quantification of just how much testing is needed in a presentation coming up. The number is rather astronomical. It actually cannot be accomplished by actually sitting in the passenger seat of an autonomous vehicle and driving all those hours and miles. We're going to find out how it is done scientifically and with certainty otherwise through testing and simulation. We're going to hear from two speakers from NovAtel, Gordon Heidinger and Lance de Groot, and one from Spirent, Ajay Vemuru. Tomorrow, as you'll be reminded frequently during this webinar, we're going to have part 2. We're going to return with more content and more information on testing and safety standards. Right now, Lori, let's find out a little bit about our audience.
Absolutely. Let's go ahead to that first poll. And on the screen, you should see what type of GNSS vulnerabilities or failures are you most concerned about? Options here: constellation failure, satellite or ground control segment, GNSS correction network failure, atmospheric induced failure, ionospheric storms or extreme troposphere, receiver failure, so hardware failure of design or manufacturing errors, or spoofing jamming. All right, looks like we've come in at 9% constellation failure, 15% GNSS correction network failure, 12% atmospheric induced failure, 16% receiver failure, hardware failure of design or manufacturing errors, and 48% saying spoofing jamming. Alan, any thoughts here?
Well, it's hardly surprising. Spoofing and jamming are at the top of everyone's mind, I think, in the GNSS world. Nearly half of the people are most concerned about this as a failure mode. With the others, the three others, statistically probably neck and neck, although less than a fifth. Each one: receiver, hardware, atmosphere, and correction network. And seems like everybody's pretty confident in the constellations themselves. But, you know, it doesn't really matter where the failure comes from if there's a failure. And we want to be proofed against all failure modes. And we're about to find out just how to go about doing that. We're going to hear first from Gordon Heidinger. Gordon is Senior Engineering Manager, Safety Critical Systems at NovAtel, Inc., part of Hexagon's Autonomy and Positioning Division. Gord holds a Bachelor's in Science degree in Electrical Engineering from the University of Manitoba. He started his career in 1998 designing electrical systems with a leading truck and bus OEM in Canada. He thrived in engineering positions at a major automotive OEM for about 5 years, specializing in design of electrical systems, vehicle electronics, and vehicle-level automotive engineering. In 2008, he transitioned to program management at several electronics manufacturers in both Canada and the U.S., leading global programs that generated several $1 billion in revenue. He continues his passion in electrical engineering today at NovAtel as the Senior Engineering Manager of Safety Critical Systems. Gordon, let's have your presentation, please.
Yeah, great. Thanks for the intro, Alan. I'd like to talk a little bit today about, obviously, the GNSS positioning systems needed for autonomous vehicles. So let's start with what we see in 99% of the vehicles today. It is several meters in accuracy, very basic hardware and algorithms, no functional safety, and IMUs. You know, they're on vehicles nowadays, mainly on the ABS and other drivability functions, but they're not really coupled with GNSS from a positioning point of view. So this is where we're at today. There's some systems coming soon, I would say, but majority of the vehicles, this is where it's at. And GNSS is mainly your navigation system, right? So it's enough to get you to your Starbucks or your favorite local restaurant. That's where the several meters it comes in, and it's good enough to get you there. So with this introduction of autonomous technology and even driver's assistance systems, we're talking anything level 2 to level 5 is where there's a real demand for augmented GNSS positioning, right? So we're going to start talking lane level. We're going to need the vehicle to know where the lane is and that it's within that range. So we're talking down to the sub-meter level and also assuring that positioning. So let's talk about how we get there, right? So walk us through a little bit of how we can get to that sub-meter and assurance. So really the big first step is enhancing the hardware. We need to talk about multi-frequency, multi-constellation. We really need to get all the data that we can. You need to have at least the dual frequency antenna and a receiver and all the things into the vehicle to get you there. And that takes you from several meters down to the meter level. Now, if you feed in some correction data, so you get correction services of some sort, and you feed that correction data into that algorithm, that'll get you into the decimeter range, right? So that starts getting into the sub-meter, and that's where you can start saying reliably that you're in the lane of the road. The advanced software now is where the really sophisticated stuff comes in. This is where safety comes in, sensor fusion to increase your availability, your algorithms and that stuff to get rapid convergence, so that way when you turn your vehicle on, it's there right away for you to be able to use. So this is sort of the steps to go from what we have in most vehicles today down to the autonomous systems for positioning. So I'm going to peel the onion here a little bit and talk about the corrections, right? So I mentioned corrections data as a critical point to get the system to work properly. There's two ways of doing this, and two common terms out there. RTK is one of them, and PPP, or precise point positioning, is the other. RTK involves having, setting up a base station, or the end user, the customer, set up a base station of some sort in a known location, and that's key. So it then will compare its measurements from the satellites to that known location and then provide a correction to that measurement to the receiver in the vehicle, or in the end, the rover, in this case, as we call it in the diagram. Important thing to note here is that's a two-way communication between the base station or base receiver and the rover. Precise point positioning, we then, in our case, we provide, Veripos and Hexagon has corrections feed that we can provide to the users. We have all the stations running and are maintaining those, very, very critical part of it. And that allows for a one-way data transfer to the vehicle, or one-way communication to the vehicle. So this really helps with the security and all those things. And that typically is done over the internet or LTE or some sort of network connection. Some limitations, obviously RTK is very precise, but you can only be 40 kilometers from the base station, so you'd have to have a whole network to get global coverage. You can imagine the headaches that would come out of trying to manage a network around the world for this sort of application. So PPP is really there globally already. So that's really, for automotive, this is really the service that we're recommending. So in the end, the results, right, we go from 5 to 15 meters accuracy at best down to the lane level. And essentially, this is really the key to enabling the autonomous vehicles. All right, let's talk about, all the different sensors. Everyone always talks about LiDAR and radar and all these things. And a frequent question we get to is, can we replace some of these with lower cost, or if we have a good GNSS receiver, what's the cost trade-off of these things? But it's really meant as a complement to it. So you can see here, all these relative measurements, or relative positioning, as we call it. So LiDAR, cameras, it's all looking at the relative surroundings, where GNSS is an absolute measurement taken on the globe type of thing, right? So it really tells you exactly where you are on the world in that position. So the systems are really meant to complement each other. They're really meant to be integrated together, especially when you start talking on the safety side of things. So this next slide here will really show, you get into these environments where there's no landmarks or no features or snow covered. I mean, how many of us have driven on roads like this, right? Recent discoveries are, as companies are developing autonomous vehicles, that are discovering that rain mist is really, really hard on LiDAR and cameras, right? You can imagine there's just this body of water in the air that's being picked up by LiDAR. It's really causing issues. So GNSS will actually perform really well in all three of those situations. So again, it's the weight of possibly maybe leaning more on your GNSS algorithm or your system to help guide the vehicle. Obviously, urban environments, and that's always a challenge we get too, is people always say, hey, how does your GNSS work in urban canyon? Well, if you block the sky, there's nothing much we can do from a GNSS point of view, but there are sensor fusions and IMUs and things that'll help you with that, but the other sensors will do really well in this situation as well. So again, it's the end user, it's that vehicle level solution that is really the point here. So let's talk about the system architecture on a vehicle. We're talking electronic control modules and all the electronics. I mean, there's hundreds of modules on a vehicle, but particularly for our solution into production, we have obviously GNSS antennas, we have the LTE antenna. There's always some form of telematics modules, usually tied to the entertainment or infotainment system. And then there's some sort of feature control module, some ADAS or autonomous driving module, and that's where your artificial intelligence will often be sitting. So our solution integrates into this very nicely, right? So we take, the measurements, the GNSS measurements and observations from the telematics module, and that is fed into the feature control module where our software positioning engine, safety rated, would then give you the feature control, right? So the output there is position, velocity, attitude, and that is fed into the vehicle control. So let's look at this closer. So from a validation point of view, all you automotive guys out there on the line, we all are familiar, and any electronics module manufacturer for that matter, all understand the system boundary diagram, right? So the device under test, right, this is why I'm just going to pick on the software positioning engine alone, right? So we look at all the inputs on the one side and we have all the outputs on the other side. So as we test, we're always monitoring outputs and we need to vary the inputs. So I'm just going to talk about the range and the observation data input. All the ranges need to be tested. So every functional range, everything that you could possibly think of as an input in the world has got to be fed into this, including how it fails, all the faults, right? So some of the value ranges we talk about here is like satellite geometry. If you're tracking 10 or 20 satellites in the sky, imagine all the possible geometry combinations there. And then think about, how they'll fail, or if you're only down to 6, what happens? Like all of that full range needs to be tested, multipath, signal and noise, and that satellite count as I just highlighted. And in addition to that, how they fail, right? So you need to understand the failure mode of each one of these, and you need to input that into your software positioning engine and see how it behaves. It needs to behave in a completely predictable and consistent manner in order to achieve that safety, right? So faults are satellite failures, jamming, spoofing, multipath, and I'll talk a little bit more about that in range. So you can imagine every input has a full range of functionality, a full range of faults. All that stuff needs to be taken care of. So integrity, there's another definition I'm going to pick on a little bit there. That's basically a study of how GNSS can fail, or the positioning solution can fail, right? We really need to understand that in order to give it a rating and to be able to make sure the performance is there, right? So ground segment failures, false orbit calculations, those are all part of it. Hardware failures up in the satellite itself, as we call evil waveforms. That's truly a definition, not a word I just made up. But if we get a waveform that has been tampered with or not broadcasting properly, that's important. Atmospheric failures, and not everybody knows the atmosphere does weird things and bends the signal and does a whole bunch of funny things to it, but it's really the extreme conditions of that. So what happens if you have an ionospheric storm that happens once in 100 years or something, and these are the conditions that really need to be predicted. Difficult multipath, and I'll talk about that in the next slide a little bit. There's some conditions in multipath that are really hard to detect. You can't just circle your measurements and say this is my safety range. And then spoofing and jamming, as we saw from the poll, this was a hot topic as well. There's a lot of ways to mitigate this and to detect it, as a matter of fact, with the algorithms that we have. Then there's your cybersecurity side, right? If someone's hacking into servers or that sort of thing, then they broadcast to all the vehicles that are on the road type of thing. So all these things are really, really important. Obviously, corrections network, we do a lot of things to make sure our reference stations and those things are all, accounted for. So in the end, the protection level output from your algorithm with integrity essentially has to cover a lot of these failures. So I'll drill down one more layer on the onion here. Just talking about like one case of multipath that's hard to talk about. And I'm going to talk a little bit about the mathematics behind that just to think about it. you remember, so on left there's a normal Gaussian distribution curve. We all remember from our statistics classes that this, that's sort of the typical curve, what it looks like. GNSS positioning, if you took the one-dimensional analysis of that, you would see that it's slightly different from a typical Gaussian curve. The tails are typically a bit higher, so they go a bit longer and wider. And when you get into a multipath situation, you actually get sort of two nodes like this, a multimodal nodes, two humps as we see here. And that's the normal understanding of multipath, and everybody accounts for that. But the tricky part is if you, let's say, block your primary path of measurement from the satellite, and all you see is the reflected path, then what happens is the true position is still here in the middle of the blue dotted line. And we have this second node that's actually misrepresenting or shifting what you would think is your true position, right? So that condition is also, a potential mode, a range of value, as this is very normal. You drive into any city. So this type of thing really needs to be understood and needs to be mathematically proven and tested, as we get onto later and today and tomorrow in our discussions. So let's step back and look at the whole onion again. I mean, think about all the variations, all the full range of operations, all the failure modes in the vehicle architecture. I mean, it's massive. We're talking billions and billions of possible conditions in the world, everywhere around the planet, in the vehicle, user errors. I mean, all these things are in and out, inputs and outputs, and that all needs to be done on the analysis, as Richard had introduced us to earlier in the talk as well. So, and typically your ASIL ratings, your safety ratings for autonomous driving is ASIL D, right? So your failure rate there has got to be 10 to the minus 8 per hour is all it's allowed to miscalculate or misrepresent. So really, really stringent safety on top of a million and billion combinations. This is really what we're faced with, and this is how we dissect it and get this get the solutions out there. So at this point, I'd like to hand it back to you, Alan, to continue on with our presentations today.
Thanks very much, Gordon. And for those of you in the audience who during the poll question at the beginning wanted to choose multipath and sent in comments about it because it wasn't offered, you saw that Gordon did discuss multipath there. We were simply limited in the number of options we could offer you in terms of answers to that question. But multipath is definitely a failure mode that is factored, and we are discussing today and will continue to discuss. We're going to hear next from Lance de Groot, Senior Team Lead, Geomatics Software for Safety Critical Systems at NovAtel. Lance holds a Bachelor's of Science and a Master's of Science degree in Geomatics Engineering from the University of Calgary. He joined Hexagon NovAtel, part of Hexagon's Autonomy and Positioning Division, in 2008. About the same time Gordon came to work. During his tenure, he's worked on many cutting-edge technology projects, including developing algorithms for ground reference receivers used in SBOS networks, high-precision positioning and relative alignment algorithms for commercial applications. His current focus is developing safety-critical software for autonomous applications. And as I said, he's the Senior Team Lead, Geomatics Software with Hexagon NovAtel. Lance, please go ahead.
Thank you, Alan, and hello, everyone. So I'm going to dig a little bit deeper into the specifics of the technology and also talk a bit about performance and testing. Typically, from a traditional GNSS system, the quality metric that you'd be used to seeing is the estimated accuracy. It's based on the propagation of variance through the position computation. You'll have some point cloud coming out of your system, and you'll get a confidence ellipse around that point cloud, sometimes a confidence circle. And you'll see these at various levels. 68%, 95% are very common. The problem with this as a quality metric is that it assumes that all of your inputs are zero mean Gaussian variables. It doesn't consider the possibility that you could have a bias on one of your observations. So if you have that, so for example, the case that Gordon was just talking about, where if you have only the non-line of sight multipath signal, and so you have a bias on this observation, what it does to your solution is it will the bias propagates into your position, and it will bias the entire output without changing any of the other random properties. And the confidence ellipse that you have doesn't reflect the shift at all, because it's made the assumption that the inputs were unbiased. So this is an inadequate quality metric from a safety standpoint, because you need to be able to catch these sorts of situations. So we need to replace it with something that can bound these positions even if there's biases present. And in high integrity GNSS, the metric we use for that is called a protection level, or PL. And essentially it's an estimate of the maximum possible error that you could have in the position at any one time. So it considers that you might have undetected biases on your measurements. It tries to provide an upper bound if that's the case. What it doesn't do is it doesn't make any claim about the distribution of the errors. It's not saying for sure that you're more likely to be at the center of the region or not. So in that respect, it's not the same as a confidence ellipse, but its objectives are different. So if I throw in a few more definitions here for integrity, we just talked about the protection level. It's the maximum possible error. It's an output from your positioning computation. You compare that against an alert limit, which is the maximum error that the system can tolerate. And this is part of your system design, and I'll talk about some values for that in a moment. So anytime your protection level is less than your alert limit, you know you have less error than you're willing to accept, and so you can use the output from that system. If the protection level is greater than the alert limit, you can't be certain that your error is at an acceptable level, and so you shouldn't use the output. So in terms of requirements, we have typically talking about an integrity risk. This is the probability that the true error is greater than your estimate of that true error, which is the protection level. Because we're dealing with random events here, that is still possible. We try to keep that very low. And this is the main safety requirement. And so here you'll typically see very, very, very low margins for this risk. The other requirement is the availability, and that is the probability that your protection level is less than the alert limit. As long as the protection level bounds the error, the system is still safe, but if it's too large, the system isn't usable. And so this is the real performance requirement. It tells you how often you're going to have output from your system that you can make use of. So in terms of what performance is required, there's no fixed standard. It's really dependent on the design of each individual system, how it interacts with the other systems in sensor fusion, and so on. A few sort of broad categories that you'll see for geogating applications, or if you just want to initialize your location for an HD map matching operation, you'd be looking at several meters. So for example, in the upper right picture here, just confirming that we're on the main road and not the side road. Several meters is adequate. For V2V, about a meter, actually 1.5 meters, 1 sigma, is the spec recommended by NHTSA. For autonomous driving, we're looking at that lane level positioning, and so the requirement on the entire system will be something less than a meter. And this is the requirement on the entire ADAS system with all the sensors going into it. The requirement on the GNSS or the GNSS INS input into that system will be different than that. It really depends on how the system is put together. Availability, probably on the order of 90 to 99%. We need it working most of the time. And the integrity risk, this also really depends on the safety concept. It depends how much redundancy you have, which types of sensors go in. You could see anything from 10 to the minus 3, maybe 10 to the minus 8 per hour. It's tempting to compare this to the hardware failure rates in ISO 26262, which are 10 to the minus 7 failures per hour for ASIL B or C, and 10 to the minus 8 for ASIL D, but it doesn't necessarily have to be the same as these, since those aren't specific to defining the risk of your positioning system. And I'll talk a little bit more about that tomorrow when I discuss the various standards. So Gord showed this slide a moment ago. We have all these failures. How do we actually account for them? A great tool for that is a fault tree analysis. So you can show how all of the different risks are allocated throughout your system. You can assess them independently, and you can sum them all up. So in this case, you can see you can break all your faults down into different categories, satellite, local, and so on. Notice there's an area here for correction fault. Because we're using corrections in these high precision applications, they themselves are a potential source of faults. And you can keep breaking this tree down until you get down to a level where you can analyze individual error sources. So bottom level might look like this. You have contribution from some individual failure, and its contribution is the product of how likely that is to actually occur, and then all the different mitigation methods you have against that. So here I'm showing, as a hypothetical example, You might have a correction service that catches 99.5% of occurrences and two different techniques in your client that are catching 95 and 80% respectively. And so that lets you bring down the probability so that when everything adds up, you don't exceed your total goal. Some errors, you may not have any help from your correction service because they're only local errors, multipath or hardware failures. And so here the client will have to take care of that entirely by itself. So we'll take a break here. I'll hand it back to Alan for some Q&A.
All right. Thank you, Lance. We'll be back for the second half of Lance's presentation. Right now, we're going to open it up to a few questions from the audience. And the first one is for you, Lance. How can we ensure that the correction service meets the required level of integrity?
It's definitely tricky. All of the various safety standards do typically make some provision for service history. So if you can show your system has worked for a long time, you can take credit for that. But because this technology is advancing so rapidly right now with new constellations coming in, new frequencies coming in, it's not likely that that will be an option. And so I think what you really have to do is you have to do an analysis of your correction service, identify its failure modes, and make sure that you have sufficient monitors added to it to ensure that your failures from the service can come down to a level you can work with. And it's really helpful if you can look at your client side and your correction service together to make sure that you've allocated the risk correctly between those two sources so you have a balanced contribution at the end.
Okay. Gord, a question for you about multipath, the option that we skipped over in our poll question, but is definitely a very live issue. No matter where autonomous vehicles will go, but particularly in downtown areas. What's the expected magnitude of the shift seen from multipath on a position in such a downtown area?
Sure. I'll interpret magnitude in two ways, so I can answer it in two ways. But the magnitude of the lobe, the probability lobe, is always a bit lower than a direct path signal from the satellite, so that there's that magnitude. But then the magnitude of just the shift in error, which I'm guessing that's what the question is asking. Yeah, that could be tens of meters. We've seen hundreds of meters actually. So the multipath can send your accuracy out the window basically in the right condition. So depending on the materials of the buildings or what it's bouncing off of, or if it's even a semi-truck next to you on the highway or something. So there's always, a wide variety of multipath conditions.
Yeah, semi-truck next to you on the highway is kind of a scary concept when you're thinking of autonomous driving, so that definitely needs to be factored in. We're going to be discussing multipath today and tomorrow, so be sure to tune in tomorrow. There's going to be a lot of content about testing for multipath. Gord, another question for you. What about all the other processes and documents required for validation and verification? Are they also key inputs to the integrity study and simulator setup, for example, like DFMEA and PFMEA and so forth?
Yes, absolutely. Those are all key documents. There's no getting around them. As a matter of fact, when you start talking safety, those are all very scrutinized, very critical, and also audited at a regular basis, right? So these documents become absolutely vital. Yes.
And does the system level or vehicle level safety model affect the safety model and architecture of the software positioning engine?
Yes, that's a great question too. We see a lot of vehicle level decisions that are made or assumptions that are sometimes false or in the end turn out to be a breach in safety, for instance. So, you have to have two ASIL BFD systems together to make an ASIL D system, let's say. And so you always have to be careful not to reuse sensors or cross-pollinate a wheel speed sensor or an IMU or something like this that's used already for, let's say, velocity. And then you use a GNSS, they have to be isolated in some cases for the safety model. So that vehicle system safety design is absolutely critical at the OEM level as well.
All right, I see a slew of more questions coming in. It's going to take me a little bit of time to order them up. So we'll return with more questions for Gord and Lance and our third panelist, Ajay, toward the latter part of the webinar presentation. Right now, Lori, let's have our second audience poll.
Okay. Coming up on the screen is that second poll. And the question here is, what level of positioning accuracy do you think autonomous driving requires? 0 to 10 centimeters, 10 to 50 centimeters, 50 centimeters to 1 meter, or greater than 1 meter? Okay, looks like we have 32% coming in at 0 to 10, 49% saying 10 to 50, 17% saying 50 centimeters to 1 meter, and just 2% saying greater than 1 meter. So, Alan, any thoughts on this?
Well, we call this a quick poll, but it's really in the nature of a pop quiz. Everybody's back in their desks in high school, and we're seeing if you were paying attention during the presentation, because we gave you the answer to it. And 49 plus 17 pretty much got the right answer, because it's right around half a meter. So from under half a meter up to half a meter, we will be generous and include the 17% that said 50 centimeters to 1 meter, because it is right around half a meter, the level of accuracy for autonomous positioning. 0 to 10 centimeters, a third of the audience chose that. That shows that there's a lot of anxiety out there about autonomous vehicles. It may be a little bit stringent, because 10 centimeters, I'm looking at it now, measuring my index finger gap, that's pretty close. Well, we'll hear more from our panelists whether we need to be that precise, but generally the accepted value is right around half a meter. Lance, let's go ahead with the second half of your presentation. Afterwards, we'll hear from Ajay and then more questions. Go ahead, Lance.
Okay, thank you. So I want to talk a little bit more about the technology before I get to some results. I showed before the break that you do need to have a lot of mitigation at the client side to protect against these faults, especially if the correction service can't help you. So what we usually use for GNSS for that is RAIM, Receiver Autonomous Integrity Monitoring. This was originally developed in the aviation industry when they started using GNSS for some of their navigation. The same techniques can be adapted to land-based applications as well, but there are a few differences. The environment is different. We have local reflectors is one of the big ones. We see different atmosphere as well. We're using corrections, as I mentioned, because these are higher precision applications, which we have to consider. We're making heavier use of sensor fusion. We may be doing ambiguity resolution to reach those positioning performance targets. And all of those things together mean that we're looking at a filtered solution. To use carrier phase measurements, we have to estimate the ambiguities and so on, which is not something that historically aviation has done. It was always a single epoch code-only solution. And this really changes things, because if you have a fault on one of your measurements, which is shown in the figure here, even after you detect that fault and you exclude it, there's some time that it will continue to persist in your filter. And so your methods have to account for that and make sure that you're protecting against the lingering effects of those errors. Okay. So there's a few techniques for carrier phase RAIM, or CRAIM as it's called. There's no standard approach yet. It's definitely an area of active research. There's sort of two main approaches that you'll see. One is to look at the residuals, so it's sort of a measurement domain approach, which is similar to classical aviation RAIM techniques. So you're trying to figure out the maximum undetectable error in those measurements and then see how that can affect your position, accounting for that persistence effect. And also solution separation is another technique, which is more of a position domain approach. And this is actually getting into aviation now as well. The new ARAIM methods are based on solution separation. And the idea here is that you compute your position multiple times using different subsets of the measurements. So if you have a fault on one satellite, in this example shown here, a fault on satellite 1, the set that doesn't use satellite 1 is not affected by that fault. And so you can see how it separates from all the ones that are using satellite 1. And that separation between your different solutions gives you an indication as to how much impact you can be having from those errors. So I'll show a few results here from some of our testing. This first set is for an open sky kinematic loop. This is a loop near the Calgary airport in an industrial region. There's restrictions on building heights because of the airport. So it's a pretty clean environment. This sign you see in the upper left there is actually the most challenging feature on the whole route. So it really is about as clean as you can get while still being driving. So this is using automotive grade hardware, a prototype automotive antenna, a dual frequency automotive receiver, and then our TerraStar X corrections and our software positioning engine. So this is the performance you see in horizontal error. The accuracy of the system is down around 20 centimeters. The protection levels are coming down to below about a meter after some convergence time. And on the right here, if you're familiar with it, this is a Stanford ESA integrity diagram. It's a plot of the protection level versus the actual error. And what we want to see here is that we're always above the diagonal, which means that we're always bounding that error correctly. And in this case, we are. That's open sky, of course. It is fairly benign. In the real world, you're going to have challenges. Specifically, a lot of these systems are targeting highway driving to begin with. And so you get frequent overpasses. And those will cause a brief outage in your GNSS. You lose your carrier phase ambiguity information. So if you're running GNSS only, this causes a larger jump in your protection level because you've lost all that information in your filter. You have to have some reconvergence time. And this is where sensor fusion really becomes useful. So the lower line here on this graph is using a GNSS INS. So the inertial can help us bridge through that gap. This is a pretty good example. You see almost no impact. You do usually see a little bit because you have some uncertainty in your inertial during that propagation time, but it really does make a drastic difference, and it's very important to improve the availability in these more realistic scenarios. So I have a video here showing what happens in a case in California. This is a highway in Silicon Valley, and the protection level is showing what happens as we go under these overpasses coming up. It's a little bit hard to see, but we're in sort of that 1 to 1.1 meter range. And then as we come under the overpasses, you will see the protection level jump up a little bit. So there we jump up to 2.3 meters, 1.5 meters, 1.2 meters. So you do get a bit of an increase because for a second or two there, you're propagating on inertial. You have to account for the uncertainty in those measurements, but that really does help us come down a lot faster than in the GNSS only case. So a word about testing. This was a very interesting paper. Essentially, the authors looked at the historical fault rates, or I guess fatality rates, crash rates, injury rates for human drivers over the years in the United States. And then they just applied some confidence testing, some probability to this to say, all right, if we're going to just build an autonomous car and put a fleet of them out there for testing, how long do we have to drive before we can be sure that we're at least as good or better as human drivers? And the result is actually quite staggering. If you want to prove that your autonomous vehicle is at least as good as human drivers in terms of fatalities at a 95% confidence, you have to drive for 12 and a half years with no failures at all. Assuming that you do have some failures and you want to build up enough to prove that you're at least as good at again, a 95% confidence level, you have to drive for 400 years. And that's assuming you have 100 vehicles driving 24 hours a day all year long, which is quite a large fleet. Gets a little bit better towards the right of this graph. Those are the intersections for looking at just injuries or looking at just collisions. But at fatalities, 400 years, which is obviously entirely impractical. So we can't just do this through live driving. How do you test it? You have to test it through deliberately injecting and stimulating those faults you're interested in, getting back to what Gord was showing a moment ago with the boundary diagram. So here's an example. This is a case where we turned off the fault detection within the filter and just let it compute a protection level, and we injected a 15-meter pseudo-range fault on one satellite with a few different cases, a step, a ramp, and then a 10-minute transient fault. And so then you can take these rare events and you can force them to happen in the lab, and you can see how your system responds to them and know that you're bounding the errors properly. So there's two ways to do this. You can do it through direct manipulation of your data, which would be appropriate for a software-in-the-loop sort of test setup, or you can do it through simulation of actual signals that contain these errors, which would be more appropriate for a hardware-in-the-loop setup, and it's what Ajay will talk about next. And with that, I will hand it back to Alan.
Thanks very much, Lance. We're going to hear next from Ajay Vemuru at Spirent Communications. Ajay's a bit of a magician because he's going to take those 400 years of testing and compress them down into about 15 minutes of webinar presentation for you. That may be a bit of a hyperbole, but he's going to do his best. Ajay is Product Line Manager, P&T at Spirent Communications. He has more than 10 years experience as a navigation engineer and has worked on various aspects of GNSS receivers, from research and development to integration and testing. He got his master's degree in electrical engineering and computer science from Ohio University. And as I said, he's a product line manager at Spirent. He helps the robotics community build safer and more reliable location-aware platforms. Before starting at Spirent, he worked as a software engineer and research engineer at two of the leading semiconductor companies in Silicon Valley in California. After a successful career researching advanced location algorithms and developing software towards improving location-based services on mobile devices, he's now responsible for launching new solutions targeted towards automotive and robotics. Ajay, please proceed.
Thank you for the introduction, Alan. Some kind words. Thanks. Right. All right, so 2/3 into the webinar, I'm sure we are all aligned that in safety critical systems, fault detection and exclusion is a critical functionality to prevent users from potential risk caused by rare sensor faults. So while fault detection function provides the ability to alarm when faults occur to ensure the integrity levels that NovAtel, Lance, and God were mentioning about, fault exclusion, on the other hand, enables receivers to exclude the faulty measurements to improve continuity, right? So this is the fundamental that we have so far understood. Now, in summary, putting together the key performance requirements and looking at the challenges, there are far too many challenges for us to really dig into. Right, so we can pick one of those that Lance very recently talked about. So he did mention the pseudo-range faults and how the fault tolerance implemented in the user equipment in form of receiver autonomous integrity monitoring could address the pseudo-range fault. Yeah. Similarly, there are so many other challenges with GNSS and so many other challenges with the other sensors that are part of the vehicle, of the land vehicle. So let's talk a bit in detail about each of these sensors. Sorry. So there are many sensors available, and each sensor has its strength and weakness, as we discussed. Now, GNSS is the only sensor that can provide absolute position, as God did bring this about. And why is GNSS the only sensor? Because it is using a global reference. It is a natural system which uses geodetic datum, whereas the other sensors do need HD map or ADAS level map to project the features that they detect onto a global scene. Why is a global reference system required? So let's pick a system which is V2V that we heard before. So a V2V system needs a common reference for communicating between two different vehicles. And how can you achieve that? As long as you are talking about the same feature in the same global reference frame, it becomes more reasonable for vehicles to understand. And for the purposes of our presentation, we will be talking about GNSS predominantly, and we will be talking about aiding GNSS with IMUs and other vehicle-based sensors such as wheel ticks. Remember the fault tree that Lance brought up? Now, how do you make sure that the integrity levels are well managed? How do you make sure that the true error does not exceed the protection level due to sensor faults, right? And this is where simulation comes into the picture with its capability of having ground truth, which is the fundamental of having, the fundamental of simulating everything. The ramp fault in pseudo-ranges that Lance brought up is a typical failure mode in GNSS and is one of the major sources of undetected faults, right? It's one of the sources, right? You do have a lot more. So for example, in a highway scenario where GNSS signals are unobstructed, there could be a possibility for segment errors which are considered as corner cases as well. Each of these will have different impact on the performance of the receiver. For example, in 2014, GLONASS suffered a system-wide outage for 10 hours. And in 2016, similarly, GPS had a timing error which exceeded the design spec. In both cases, it is not a receiver design error, but it's a system issue which needs to be still considered, and the corner cases have to be reproduced and tested against the integrity levels. There are reports which say that some of the receivers used the autonomous integrity monitoring software to isolate the errors, but the others which did not use them did notice huge clog bias estimates, which in turn made the receiver to not track any of these measurements, right? Now, as discussed, these errors can impact the performance in relatively open sky environment, where GNSS is known to work very well. What happens when a user in an environment that is known to have challenges, like for example here, overpasses and partial blockages of GNSS satellites are known to pose more problems than a completely denied environment such as tunnels. The challenge of nav engine or the fusion engine now is actually to identify such scenarios, deweigh the GNSS measurements so that greater trust is put on measurements from other complementary sensors. Now, these challenges are happening more and more, and we need to make sure that these are completely taken into consideration. And this is one area, again, where simulation comes in handy to speed up your test cycle. So this leads us into using more sensors along with GNSS, which means these additional sensors also come with their own challenges, which means it increases the probability of things going wrong with individual sensors by themselves and with a combination of these sensors. Right, so as you can see, IMUs come in different flavors. Consumer grade to nav grade, each at a different price point and various quality levels. Not all IMUs are really created equal, even within each of these above segments. Each IMU has its own strengths and could be addressed or designed to address a certain tailored need of a specific application. These different sensors also have to have a standard means of reporting specs, which there is no standard means. So for example, let's just pick that a nav grade sensor or a tactical grade IMU, which on their spec sheet typically talk about angular random walk, velocity random walk, gyro bias, and axle bias. Whereas the MEMS inertial sensors, they only predominantly talk about the angular random walks and velocity random walks. Now, some vendors do provide the bias values, but the bias values are so huge and there is no repeatability of those bias values that these numbers cannot really be used in meaningful ways. And not to mention about the different formats and the data interfaces. Right, so with that said, teams designing navigation filters for safety critical systems need to be mindful of the kind of IMU to be modeled. For example, if a high-end IMU is being considered for design, only bias drift and random noises should be or can be considered as filter states. Bias drift is typically modeled as a Gauss-Markov process. Whereas for low-cost inertial sensors, MEMS, the bias and scale factor should also be considered in addition to the previous states. So everything becomes critical. You have to take into account all the different parameters, all the different things that can go wrong. And although these inertial sensors are fully self-contained, the measurement of these accelerometer and gyro are affected by different errors, which can be put into different buckets, deterministic and stochastic. Deterministic are defects from manufacturing and installation, whereas stochastic are more random due to the random variation of bias or scale factor, or whatever you say. The additional factor that also needs to be taken into account is the temperature. So how do you play around with all of these errors on one single sensor? This is again one of the areas where simulation comes into the picture. Simulation can allow design teams to inject the right IMU faults to the test and estimate how the navigation performance is working, or how is it tolerant to these injected faults. There are too many parameters to keep track of, and tuning the filter to a certain use case is critical. So here's one use case. Yeah, so we briefly touched upon this in a previous slide. So what we've done is we need to model our nav filter appropriately based on the quality of IMU used. What happens if you don't model it right? So for example, look at the plot here. This is what happens when you model your nav filter with high-end IMU with the assumption that it's going to be working along with a high-end IMU, but in reality, a lower-end IMU is used. In other words, it's a wrongly tuned IMU. Yeah, so the effect of having IMU being noisier than it should be is what you can see on the picture on the left-hand side on a KML. So this is a snapshot of 5 passes through that path. And in red is the case where the IMU errors were not modeled correctly in the filter, in the nav filter, and green is where the error is optimally modeled. You can notice that the green trajectory has a tighter scatter across the 5 passes compared to the red. Right, and you can, on the plot on the right is actually where you can see the magnitude of the errors for the corresponding KML. Let's look at another example. Right, this is where IMU axes are mismatched. You can see 2 passes through the tunnel where the trajectory diverges from the truth. It's not a full tunnel, it's a nearly full blockage. And so during these periods, the solution is only running on IMU, and the orientation error causes this issue, causes this fault. In other regions, when there is GNSS, the GNSS data or measurements dominate the orientation error, and it is not, and the error, the position error, is not as apparent. So I think the bottom line is it is also important to note that the fault detection and exclusion schemes that are being developed need to not only focus on the faults in the current epoch, but also take into account any possible undetected faults from the previous epochs. Because these undetected faults could impact current time innovations and the state estimates. Now, let's move over from the IMU and see how other sensors, the other sensors that are vehicle-based, for example, the wheel ticks, are going to impact the nav filter. So just a quick intro, an odometer is an electronic device that generates an integer number of digital pulses every time a wheel on the vehicle makes one revolution. Yeah, these digital pulses need to be translated into distance traveled, however, right? So that translation needs to be done. That's when the scale factor comes into play. And these, as you can imagine, the scale factor is dependent on the kind of vehicle, because you need to take the parameters such as the wheel radius, the pressure, the temperature, the tread depth, and the speed. All of this has to be taken into account to predict the distance. So this is all captured in research. So scale factors are known numbers for each of these vehicle types, but the issue is the errors on the scale factor itself could be random errors, right? And the drift in the odometer scale factor and the quantization error will show up as false and end up in position error estimate that is computed using odometer information. So that's something that we also have to keep in mind. So those are some additional faults that we have to take into account. Not just that, there's another error which is more important to take into consideration, which is the wheel slip. And this needs to be modeled correctly because it is due to the measurements that are slowly diverging from the true state that the wheel slips happen. And the impact of wheel slips on position is also significant. I mean, for more in-depth analysis, the reference at the bottom is one good piece of paper where you can really get more insights into how this can impact the overall position error. So putting all of these together, we need to take advantage of all of these sensors available on the system. Everything that we have spoken so far about, GNSS, IMU, wheel ticks, mag and magnetometer and barometer, we did not have enough time to really touch upon. But there's enough research available. Please let me know if you do have any questions or concerns regarding that. But with all these sensors, we need to be able to systematically design our nav system so that it is tolerant of any faults that may produce large position errors. As we know, these faults that affect in current time do have impacts on the future as well. So it's very important to take everything into account, which means there is a critical need to validate the system under a combination of various sensor faults, and simulation is the right place to go. Now, with all that said, there is one other important consideration that we have not talked about so far, which is the vehicle trajectory and what is the impact that it might have on the navigation system overall. So, for example, let's consider how frequently the vehicle turns, how fast the vehicle moves, and how frequently it stops. All of these do have all of these do have an impact on the position accuracy of the overall system. This is easily noticed when you really see that a rate gyro scale factor error contributes more to a heading error when the vehicle turns, or the magnitude of the error caused by the odometer depends on the vehicle speed. Right? And if the vehicle comes to a complete stop, it's probably possible to estimate the rate gyro bias because we know that the vehicle is stationary. As these examples illustrate, the contribution that some sensor errors make to the accuracy of the system's position estimate can vary with the vehicle's motion. And hence why all of these have to be taken into the picture when you're running an analysis and when you're trying to compute the integrity levels of the protection levels. So the benefit of simulation is that the specific test scenarios can be created in software while sitting in a lab, which means it is feasible to obtain the true values to compare with the system solutions for your overall algorithm evaluation. I don't want to get into the details, but I think it is really important to understand that a good simulation environment will be able to give you the right levers so you can add the right errors or faults that can be modeled and that can be designed to be mitigated. It is really important that you choose the right simulation environment or the platform. You don't want to be in a position where you don't know if the source of your position error is due to the simulation issue or a nav engine performance issue, right? So we at Spirent do take extreme pride in designing stable simulation platforms for every sensor that is being simulated within our platform. We are being used by industry's leading research groups and have been confirmed to meet their tight simulation criteria. Here are some references that can help you understand how and why we are being used across the industry. In conclusion, the integrity risk evaluation is important in safety critical systems because the navigation system is designed to meet expected levels of integrity, and it is expected to provide its users with timely alerts when the system cannot meet these integrity requirements. There is no better way to evaluate integrity risk than in a reliable simulation environment. It is very important that you choose the right simulation environment so you can focus on your development rather than debugging the simulation tool itself. With that said, I'll hand it back to Alan, and thank you for your time.
Thanks, Ajay, for that great introduction to simulation. I want to emphasize to the audience that this is an introduction and beginning exploration of some of the issues found in simulation. We'll be back tomorrow, same time, same channel, with more on simulation. And we'll also explore the different standards of automotive safety and autonomous safety. So be sure to get back with us tomorrow for more of this high-value content. We're going to have more questions from the audience in just a minute, but Lori, let's first find out some answers from the audience to our question.
All right, and there on the screen is our third and final poll for today. Question is, what type of IMU errors are you most concerned about? Bias stability, scale factor, axis misalignment, angle, velocity, random walk noise. So it looks like we have a majority, 44% saying bias stability, 4% scale factor, 19% axis misalignment, and 33% angle, velocity, random walk noise. Alan, thoughts here?
Well, I'm going to keep my rather impoverished thoughts to myself because I'm not an IMU expert. I'm going to defer to Ajay on that. Actually, Ajay, we have a number of questions have come in regarding the IMU that you just began to talk about. So I'm going to give you the chance to return to that, and we'll have questions for the other panelists as well. But first, AJ, how representative can the IMU measurements be in a simulation environment?
Right. So they can be. The short answer is they can be very representative. Now, the long answer is it really depends on the amount of information that we have access to. So the more information we have access to about the IMU itself, the spec itself, the better we can model the IMU, and we can add that in a simulation environment.
And does Spirent have a library of supported IMU models and vehicle dynamic and trajectory models?
Right, that's an interesting question. So again, in short, yes, we do have a library of supported IMU models. And what I should also probably stress here is that we do have a model where even though we don't support one of those IMU models, we can still provide those IMU models as a service, one, or we can open up our interface so customers can come up with their own models of IMU and they can inject that into our simulation environment, which means it's pretty much like an I don't want to go out and say open source, but it is accessible for customers to really change the parameters and see how the performance would be if they have a better representative error model of their IMU.
All right. And AJ, would you have any opinion or perspective on our audience poll where 44% said bias stability was their main concern, with angle, velocity, random walk coming in second place and the others trailing further behind?
Yes, definitely. I mean, I can definitely have my own perspective. So that's an interesting result, because if you're only concerned about the bias stability, I would be assuming that you're more interested in picking up a mid-grade IMU sensor rather than the cheaper MEMS IMU grade sensor, because depending on which sensor you pick, and that was one of the topics that I covered, depending on which sensor you pick, you have to be careful about taking into account the different error models when you're simulating it. So that's definitely an interesting perspective for me to really observe.
All right. Lance, harking back to your presentation, is the performance of GNSS enough to meet the requirements for lane level positioning?
I think not on its own. And that's both the accuracy performance as well as the availability. As Gord mentioned, there's that trade-off between environments where GNSS does well and where other sensors do well. And also, as we saw in the results I showed, at protection levels we're getting down to a meter. It's higher than that when you have more obstructions. I think by itself, GNSS would not be enough, but the key point here is that you have a bunch of different sensors that are coming together in a fusion to do this autonomous driving application. And I think in that context, GNSS is at the level where it can really contribute to that solution effectively.
All right. Question for Gordon. Gordon, one of the audience writes in, I expect multipath can be mitigated by combining GNSS signals, corrections, IMU measurements, and vehicle wheel speeds with raw camera pixels. Cameras do exceptionally well with pose estimation in cluttered environments where GNSS suffers. What do you think about that?
Yeah, it's a fantastic question. And let's talk about the safety of that, right? I mean, ultimately, like I had highlighted in my presentation, that two ASIL BFD systems, for example, combined will create your ASIL D functionality or functional safety. Now, if we want to take that camera input and say that's, one of the ASIL BFD's inputs, the trick would be to obtain the ASIL B rating on that camera. I imagine, can you imagine what the boundary diagram would look like? And I did one example or a concept boundary diagram of a software positioning engine, but imagine what it would look like for a camera of all the different things a camera needs to see and do that pixel, what's the full range of all the different materials, colors, objects, shapes, size, all these things that it's picking up as speed measurement or pixelation measurement. How do you safety rate that? How do you certify and then do the faults of those, right? How do you figure out the failure modes of what the camera will or won't pick up? That would be a massive challenge to rate the camera. But I mean, legitimately, if you can get an ASIL BFD rating on your camera, then that would be a legit speed signal for sure. We've done some work with LiDAR, particularly, and it works just as well as well. So,
ASIL B on the camera. Lance, we've had a number, you mentioned protection levels. You introduced that concept, and we've had a number of questions, people asking one variant or another on this. How do you compute a protection level for GNSS, INS fuse solution, or basically any protection level? How do you compute it?
Sure, I'll tackle the first part of that first. A GNSS INS fused solution is essentially the same as GNSS solution with a bit more information. So the same techniques can be used. You're still looking at all of the GNSS error sources and making sure that you understand those and have monitors in place and can propagate those variances. And then as well, you have all the inertial inputs, so you need to understand the faults on those, make sure that you have appropriate a priori variances and account for any possible failure modes. With INS, it's nice because they're internal to the vehicle. You don't have all these sort of less predictable error sources externally you have to worry about. And so many manufacturers now are looking at bringing out ASIL-rated IMUs, which will help constrain that error space. In general, the goal of a protection level is to try and figure out what is the worst possible impact on your output, be it position or feature recognition or whatever you're doing. What is the worst possible impact on your output based on what might be in your input? And so you do that by having some sort of fault detection in there and then understanding the limits of that fault detection so you know what is the level of unknown fault that might be getting into my system. And then you can see what the impact of that fault is on the output. That's sort of the measurement domain approach, which I described, and then, or as I said, there's the solution separation approach where you can try to structure your system to try and observe those faults directly by having aspects of it that are not affected by the fault. So the same techniques will work, and you could apply them to any estimation, any filter. It's just the pedigree of them is from GNSS.
All right, thank you, Lance. Gordon, another question for you. Talking about PPP. Is a PPP algorithm dependent on good satellite visibility? Is it as efficient in an urban canyon as it is in an open sky area?
Yes, PPP is, the measurements are coming from the ground stations, and those are always put in good visibility, and then it figures out where you are, and it corrects most of the atmospheric errors or properties in that atmosphere in your area, wherever you are. And so multipath is not really relevant to that. However, it doesn't solve multipath, but it does help you in multipath for high-level description on that. It's just as efficient, but again, it's not it'll make your signals that are directly from the satellites, even better, and correct those. So it does help the multipath, but it doesn't cure it, so to speak. So hope that answers the question.
Yeah, we have another question about PPP, and the audience member directed this one toward Lance. Why is it necessary to resolve integer ambiguities with PPP? If the accuracy requirement and protection levels can be achieved with a float solution, why should an OEM implement integer resolution, particularly in a cluttered environment with overpasses, tunnels, and tall buildings?
That's a really good question. I agree. I don't think that that ambiguity resolution is necessary, and I didn't mean to imply that with my slide. It may be necessary depending on the performance requirements of the application. What ambiguity resolution brings you is a faster convergence time, and especially a faster reconvergence time. But there's a safety cost with that. If you're resolving ambiguities, you have to be sure that you're resolving them correctly. And if you resolve them incorrectly, that's one more failure mode that your system has to protect against. And it's actually a really scary failure mode, because once you resolve an ambiguity, the filter then trusts that value very heavily over the inputs it's receiving. And so it's hard for it to kind of realize that it's made that mistake and correct for that. And so it's a very dangerous failure mode. So in my opinion, you're better off sticking with a float solution from a safety perspective, as long as it can meet the requirements of your application. And you should only be considering moving to PPP if there really is no alternative based on the performance requirements. But if you do that, you have to be prepared to relax your safety requirements because of this increased risk.
All right. For Ajay, in adding several sensors together, the probabilities arise to have a case of simultaneous multiply occurring faults. Can you expand or elucidate on this a little bit, a solution to this kind of problem?
Yeah, absolutely. Right. So yes, adding more and more sensors, there will be an increase in probability to have a multiple of these occurred faults simultaneously, which is true. And this is how, and this is why, you should be using simulation environment, at least to begin with. And all of those errors, all of these sensor models that I have talked about, all of these can be simulated using Spirent simulators or the Spirent environment. And the user does have all the flexibility to add or inject multiple simultaneous faults. Or if a user is too busy, we can definitely help users to come up with a test scenario or a test plan to achieve and inject these multiple simultaneous faults.
Okay, and turning to those further questions about PPP, Lance, can PPP help with simulation?
Scintillation, you mean?
Sorry.
Yes.
Yeah.
So yeah, ionospheric scintillation, it can help if you have ionospheric monitoring in your correction network, which for the applications we're talking about here, you probably do, because in order to breach faster convergence times, you need to have regional atmosphere corrections in your corrections. And so if you have that, it means you have your base stations are monitoring the ionosphere. It means that you can notice the effects of scintillation on the base stations, and you can communicate that information to the user somehow. Is it foolproof? No. It'll have some risk. There's both latency as well as the scintillation the user experiences will not be the same as what the network experiences, because you're at a different location. But in general, you'd be able to see that there is scintillation occurring across the region. You know the ionosphere is more disturbed, and you can react to that.
Okay, thank you. I want to remind our audience out there that even if we did not get to your questions during the webinar, many of them can be answered, and I'll be furnishing them all to our panelists so that they may perhaps pursue with you separately. Again, we will be back tomorrow with part 2 of our presentation on autonomous Vehicle Safety, How to Test, How to Ensure. Tomorrow's presentation will be sponsored by Spirent. We will continue to have speakers from NovAtel Hexagon. We'll have more from Spirent, and as you might expect, we will go deeper into the various aspects of simulation for autonomous safety. And we will be looking at, with Lance, we'll be looking at the standards, both the existing standards and the emerging standards that are coming into focus to help define autonomous vehicle safety. I'm going to go around our panel and ask for concluding comments, each in turn in the order of presentation. Gord, a few last words for the audience?
I really like the results. The polls look good and in line with what we were discussing. And yeah, thank you for the opportunity.
All right. Lance, last words?
Agreed. It's encouraging to see that people seem to be kind of aligning more so than would have been the case maybe 2 years ago when this started out, and some very interesting questions as well. So thank you.
Good. And Ajay, final words from you.
Thank you for the opportunity, and Spirent is always here to help in case you have any issues with integrity testing or PNT testing overall.
All right. Thanks to everyone in the audience for attending. Once again, if you're not tired of hearing from me on this topic, we'll be back tomorrow with more content. Ajay will be with us again, Lance will be with us again, and we'll have a new speaker, Ali Soliman from Spirent, and we'll go deeper into simulation. For now, that's it. I want to thank our sponsor for today, NovAtel Hexagon. I want to thank all our panelists, Gord and Lance and Ajay. And with that, back to you, Lori.
Okay, just a thank you for joining us. And this is Lori Dearman saying, hope I see you tomorrow for day 2. Bye for now.